Hello, everyone. My name is Ehsan Ebrahimi. I'm a PhD candidate at Utah Water Research Lab at Utah State University. First of all, I want to say I'm really honored to be selected for this award, and I want to thank my supervisor, Dr. Shuai, and our research partners at RTI, Dr. Triana and Dr. Bakar, for their immense help in this research. I'm going to present our research on the extended hydrofabric framework. In this research, we developed an automated and reproducible framework that extends the national reference hydrofabric by integrating water management infrastructure and operational and administrative data and to advance water management modeling. As you all know, river basins are not only purely natural systems. Human activities such as reservoir operations, diversions, water rights, interbasin transfers can modify stream flows and impact water availability. Most hydrologic models, including National Water Model and National Hydrological Model, has limited representation for these human activities. Aside from modeling capabilities, one major limiting factor is the lack of standardized water management infrastructure and operational data sets. Current modeling of water management workflows are fragmented and project-specific. For example, each state has its own water management model and data repository, which leads them to be difficult to reproduce and time-consuming. To address these limitations, we developed the extended hydrofabric. This framework extends the national reference hydrofabric by integrating three major categories: reservoirs, diversions, and water rights. Our goal was to create a model-ready structure that supports efficient storage, coring, and direct integration with water management models. We developed automated workflows to generate two key outputs: the extended hydrofabric, geospatial data product, and a relational database to organize administrative and operational data. Together, these creates a pathway for constructing and coupling water management models with existing hydrologic frameworks. For example, we can use the inflows generated by a hydrologic model as inputs into a water management model to simulate human operations. Here you can see the general steps of creating the extended hydrofabric. Process starts with collecting and harmonizing data from different sources, including WADE, ResOps-US, GRAND, and diversion datasets. Next, we perform spatial linkage, where water management infrastructure are connected to the hydrofabric segments using persistent COM-ID identifiers. Next, the workflow automatically populates a relational database that stores operational and administrative information while preserving the established relationship between these water management nodes and the reference hydrofabric segments. One of the critical challenges that we faced when developing the extended hydrofabric was the accurate linkage between these infrastructure and the hydrofabric segments. Our objectives were to ensure hydrologic consistency preserve network topology, and enable automated integration into the water management models. For points of diversion, we used a tiered algorithm. First, we used a GNIS ID match because these identifiers provided the most reliable connection between diversion records and stream segments. Then we used stream name matching after normalization. And as a final fallback, we used nearby higher order streams to preserve the hydrologic plausibility. For reservoirs, we prioritized lake pond segments, GNIS name normalization, and used distance-based matching when there were multiple candidates present. All edge cases using final fallbacks were flagged for manual inspection later. The next challenge was organizing large volumes of operational time series and administrative data. So we developed a relational database that connects these information with spatial topology. Here you can see the scheme of the relational database we designed, including its different tables and their relationships. This structure has several benefits. Standardized data organization, scalability to larger domains, reproducibility and automation, efficient querying and retrieval, interoperability with different modeling frameworks. To demonstrate the applicability of the framework, we implemented the extended hydrofabric for the entire upper Colorado River basin. We successfully integrated over 1,300 diversion points and 37 reservoirs. You can see the extended hydrofabric and its components in the figure for the UCRB. And for the diversions, 82% of them used GNIS ID match, 10% used GNIS name matching, and only 8% used a final fallback linkage. For reservoirs, 78% used direct match, and we validated all the connections made manually. These results demonstrate that the framework can integrate heterogeneous water management data sets while maintaining hydrologic consistency and minimizing manual intervention. So, to demonstrate the support of the real modeling application, we constructed a ModSim model for using the extended hydrofabric for the Colorado River headwaters. You can see the ModSim model in the figure, and in the zoomed-in figure, you can see, I hope you can see the diversion points as the purple squares and reservoir node as red triangle. As you can see with the arrows and links, the model represents the flow network topology from the reference hydrofabric. Reservoir nodes and diversions are included, and they are automatically parameterized with operational information from the relational database. To provide hydrologic inputs to the water management model, we integrated inflow time series from the NHMPRMS hydrologic model. And this first demonstrates that we can use the extended hydrofabric to construct an operational water management model. And second, and importantly, because we inherited the reference hydrofabric, we can easily couple this with the national scale hydrologic model. Now I want to briefly show a sneak peek of our current ongoing research that builds upon the extended hydrofabric. Using a model setup with reservoir operation, we test the performance of the coupled MODSIM model at the watershed outlet and compare it with two NHM PRMS models. First is NHM by HRU calibration, which calibrates individual HRUs with water balance variables. And second is NHM by HWObs calibration, which is fully calibrated with gauge observations. Initial simulations suggest that the MODSIM coupled configuration improves performance relative to the by HRU configuration, and in several locations produces performance that is close to the by HWObs configuration, despite no calibration and only adding reservoir operations. We believe with additional testing, adding diversions, more robust routing, and calibration, we can refine the coupled framework performance while accounting for the realistic water management operations that happen in the watershed. Going over the other gauges in the watershed, we see the similar behavior in the main stem, which is the Colorado River, and also on tributaries that have a reservoir present. So we believe with more refinements, we can improve the performance across the entire watershed. So the extended hydrofabric framework showed strong potential, but implementing it at HUC2 scale, basin scale revealed some important challenges. The first challenge was data heterogeneity across states. Water management data are maintained by multiple agencies, each using different formats, naming conventions, and reporting standards. Cross-state integration required extensive harmonization workflows. The second challenge was incomplete and inconsistent metadata. Many diversion records lacked persistent identifiers or consistent stream naming. For example, here in Utah, the diversion records were tied to diversion gauges, not the actual point of diversion, which created many problems for us. We believe addressing these challenges would require an immense and extensive effort from different agencies, states, and probably at federal level. These challenges highlight that advancing water management modeling is not only a modeling problem, but also a data standardization problem. To conclude, this work introduced the extended hydrofabric framework as a standardized and scalable approach for advancing water management modeling. We extended national reference hydrofabric by integrating water management infrastructure, operational data sets, and administrative information into a unified and reproducible structure. We implemented the framework for the upper Colorado River Basin, generated an operational water management model, and tested the feasibility of coupling water management and hydrologic model. Looking forward, this work establishes a foundation for future larger scale coupled hydrologic management modeling and supports broader efforts towards reproducible water resources analysis in the CONUS. Thank you very much for your time.